In the last video, we discussed how for a very long time it was believed that light existed only as a wave, that it did not have any kind of a particle nature. But Einstein discovered in the early 20th century that light also can sometimes behave like a particle, which we call a photon. And I know I'm skipping over so much science here, and just that in that one sentence, it's paraphrasing like an entire PhD degree times 2 and all that stuff. But we are keeping it relatively light and not too in depth here in this chapter. So just for now, we will just say that light sometimes behaves like a particle, which we call a photon. So then that begs the question, is light a wave or is it a particle? Because according to science up to that point, you couldn't be both. But as we find out, you can. You can be both. It is both a wave and a particle. It just depends on what it's doing. It depends on what it's doing, it depends on what it's interacting with, and it depends on what or who is observing it. It depends on a varied number of things, whether it will behave like a particle or a wave. This is what we call particle-wave duality, where something is sometimes a wave and sometimes it's a particle. It just depends on what it's doing and what's going on. So let's talk about light some more here. Let's talk about the different kinds of light, different flavors, if you will, of light. Now, realistically, light is not naturally just cut up into different sections like this. We've done this for our own benefit here. We've separated light into different regions, but in reality, light is just a literal spectrum. It goes from very, very long wavelengths to very, very short wavelengths, very, very high frequencies and very, very low frequencies. And those are always going to be opposite of one another, the frequency and the wavelength. So if you notice here, we have our electromagnetic spectrum. And if you look at the wavelength, starting down here, we have very long wavelengths. These are in meters. So this 10 to the 5 meters, that is literally thousands of meters would be the wavelength. These are what we call radio waves, and those go all the way up to, centimeters or so. That's where we get into microwaves, which are smaller wavelengths. Infrared radiation is getting into right at the edge. There's the millimeter up to micrometer or so wavelength light. Visible light is just a little sliver right here. That's all we can see, is that little bit of the electromagnetic spectrum. And inside of that little sliver, we have all of the colors that we are able to see with our eyes, starting with the reds, which have the longest wavelength at around 750 nanometers, so that's 10 to the negative 9 meters, all the way up to the purple colors up at 400 nanometers. And so the different colors are just representations of these different wavelengths or frequencies of light. So ultraviolet comes after that, more energetic than violet light. This is what gives you sunburns, as we'll talk about in just a second. X-rays are after that, even more energetic, and then gamma rays. Gamma rays, super deadly. Keep away if you can. I do want to point out one other thing here that I mentioned just a second ago, but I want to point it out again before we start talking about each of these individually. So going from right to left here, the wavelength decreased. We started with the absolute longest wavelength, and we went to the absolute tiniest little wavelengths over here. The opposite is true for frequency. Frequency and wavelength are flipped. They are inversely related. Over here on the left side, we have very low frequencies, and over here on the right side, we have very high frequencies, very high energy photons. And this should make sense if you think about what light is doing. So let's say, for example, that it takes light 1 second to move the distance across your screen here. Now obviously it doesn't take light 1 second to do that, but just for the sake of argument, let's say that it takes light 1 second to move all the way across the screen. And it doesn't matter what kind of light it is. Whether it's radio waves or gamma rays or purple light, doesn't matter. All light moves at the same speed. And so if you have a radio wave, it might only go through like one iteration of the wave through that whole distance because the wavelength is so long. So because it only goes through one iteration of the wave, its frequency is very low, especially relative to something like an X-ray maybe, where its wavelength is so tiny that it doesn't go through one wavelength over this distance. It goes through a whole bunch. Let's continue that on, all the way across. It goes through a whole bunch of those over 1 second, and so it's bouncing up and down as it goes across there through that distance. So it's going to go through a bunch of iterations of the wave over that distance, which again, it travels in the same time period. Obviously, I can't write that fast, but it goes through that same distance in the same time period, and it goes through many more of its wavelengths because its wavelength is shorter. And so it has a much higher energy because of that really high frequency. So this is why they're inversely proportional. The really large wavelengths are very low energy light. The really short, really tiny wavelengths, very high energy light. All right, so let's talk about each of these individually here. So gamma rays and X-rays, these, like I mentioned a second ago, extremely high energy light, especially the gamma rays, but the X-rays are dangerous as well. Gamma rays, we don't really have a practical use for them, not that I'm aware of anyway. I'm sure someone somewhere has some use for gamma rays and I just don't know about it. But they're definitely, less useful than X-rays. X-rays, while they are still dangerous, because they're so energetic, they can move through tissue relatively easily. So they can travel through your body, and most of the X-rays will go through. Most of the X-rays will not interact with your tissue. It will just fly straight through you. Now, the X-rays that do interact with you, because not all of them will fly straight through you, those we do tend to worry about because they have enough energy that they can ionize your DNA, which is a bad thing. But the chances of that causing some very dramatic, significant health problem is relatively low. Your body has mechanisms for fixing that when it happens. If your DNA gets damaged, then your body gets rid of the damaged DNA and it replicates new ones from undamaged DNA. But obviously there are situations where that doesn't work as planned. But it's relatively low enough danger to get a low dose of X-rays that we use X-rays to image bone. Bones are more dense than tissue, and so the relative number of X-rays that go through bone is smaller. There are more of them that get scattered, that bounce off of the bone instead of going through, and so we're able to image bones especially well using X-rays. And we could do it somewhat with other things as well if the density of the material we're looking for is different than the density of the other material around it, but it's mostly used for bones. Ultraviolet light is less energetic than X-rays, but it is still energetic enough to damage biological tissue, especially UVA. I get A and B mixed up sometimes, so you can correct me if I'm wrong, but I believe UVA is worse than B. But regardless, both of them can cause biological tissue damage, hence the sunburns when you get a sunburn, that is UV light burning you. And I've had some really nasty sunburns over my life. UV light is not my friend. Visible light is actually right next to UV light. So the violet light on the visible spectrum butts up right next to ultraviolet light. The violet and the blue light has more energy than the red light, which is why you hear all kinds of advertisements, or at least I do. Maybe you don't hear these advertisements. But I get advertisements all the time about, oh, you need blue light glasses to filter out that high energy blue light. I was like, yeah, I probably should, but I don't have any. Probably. Because especially now with everything moving online, I look at screens all the time, which is not a good thing. So visible light is not energetic enough to damage biological tissue, but the blue energy, the blue light and the purple light, those are high enough energy that they can kind of wear your eyes out. Like your eyes get tired of seeing that all the time because it's higher energy light. Infrared is most commonly used in night vision goggles. This is because objects that are near the human body temperature actually give off infrared radiation. This is a phenomenon that we call black body radiation. So you, right now, sitting in your chair, or I don't know, maybe you listen to these lectures while you're jogging or something. I don't know what you do, but wherever you are glowing. You are literally glowing. And not just because you are a wonderful person, and you've been really trying your best recently. Not because of that, although all that's wonderful. You are glowing because you are at 98.7 degrees C, thereabouts, and everything at that temperature gives off infrared light. That's just the way the universe works. Again, we're taking a very, very surface level look here. I wish I could get into more about black body radiation and the cool stuff that it does, but just for now, we'll just go with we have black body radiation, and you actually glow in the infrared spectrum, which is why in all those movies where they have the infrared cameras or whatever, they can see heat. Essentially, that's what they call them. They're looking for heat because anything that's around the same temperature as the human body gives off that radiation. All right, microwaves. So microwave radiation, that's the next lowest energy after infrared radiation. These are most often used to heat up food, and it is like the microwave in your kitchen does actually use microwave radiation. The way that it works is the microwave radiation actually excites the water molecules. Not in like a, hey, we're going to go see a movie, get excited, not that kind of way. The microwave radiation, when it impacts the water molecule, it has just the right amount of energy to cause the bonds in the water molecule to vibrate and rotate very, very vigorously. And so that movement, that absorption of the photon that creates movement, heats up the water, which then heats up all the food around it. It also works on other things as well. So microwave radiation can also interact with like certain ceramics and things like that. So if you put a plate into a microwave and just, a plate with nothing on it, and you just run it, it can heat up. It's not just water that microwaves interact with, but that's the main thing when you're microwaving food anyway. The main thing they interact with. So the last one here is radio waves. These are the longest wavelength of all the radiation in the electromagnetic spectrum. And so because of that, they also have the least amount of energy. So radio waves are often used for radios, obviously, but also sometimes for TVs and cell phones, although modern day cell phones actually use microwaves more than radio waves, just because you can put more information into microwaves than you can radio waves. let's look at a quick example here. So example 9.1 asks us to arrange the three types of electromagnetic radiation, which are visible light, let's see, X-rays, and microwaves, according to their relative wavelengths, frequencies, and energy per photon. So we're going to have wavelength. That's what well, I kind of didn't realize the edge of the screen was right there. Let me try that again. I'll put it over here. So we have wavelength. That's what that kind of upside down looking Y is. That's the wavelength. Frequency is often written as this kind of weird looking V. And then we'll just have E for energy. So the energy per photon. So why don't you pause the video, go back and review the electromagnetic spectrum, and arrange each of those three. And you can just put like 1, 2, and 3. That's all we're going to do here. 1 being the highest amount of the property, so the largest wavelength, the highest frequency, and the largest amount of energy, and then 3 being the smallest. So go ahead and pause the video and give that a try. Alright, so I hope you gave that a try. If you go back and look, we had, if memory serves me, microwaves, visible, and X-rays. Double check that, yes, visible, X-ray, and micro. So, if we're looking for their wavelengths, the longest wavelength would be microwaves, because the longer wavelengths are over here on the left side. So it would be microwave, visible, X-ray. So microwave would be 1, visible would be 2, X-ray would be 3, in terms of the length of their wavelength. Now, I'm not going to go back to that slide again, because I have all the information I need at this point to fill out the other two. Because I remember that the wavelength and the frequency are inversely proportional. So the larger one gets, the smaller the other one gets, which means that my numbering is just going to be flipped. So I'm going to have 3 here, 1 here, and this one's still going to be in the middle. Microwave has the longest wavelength, which means that it's going to have the smallest frequency. It takes more time for that light to go through the same number of iterations of the wave versus something like X-rays, where the wavelength is really tiny, and so you go through a lot of those wavelengths really fast. So then the last one here, the energy per photon, is actually going to be exactly the same as the frequency, because energy and frequency are proportional. The higher the frequency, the higher the energy. And so it's just going to be the same as the frequency. All right. We're going to call it there for this video. In the next one, we're going to talk about the Bohr model, which was one of the first models of the atom that was proposed that actually got pretty stinking close to being correct. It's not actually correct, but it still works really well. And so we're going to talk about the Bohr model in the next video.